In today's lesson, we'll be looking into momentum and the conservation of linear momentum. We define momentum as the product of an object's mass and its velocity. Hence, to calculate an object's momentum, we use the equation P is equals to m times v, where P is the object's momentum, m its mass, and v its velocity. Please note that momentum is a vector quantity, and this simply means that it will have both magnitude and direction. Also note how the unit used for momentum is kilograms meters per second, which we can infer from the very equation itself, since remember P is equals to m times v, where m is measured in kilograms kgs and velocity in meters per second ms to the power of minus 1. Then the product of m times v will be kilograms meters per second. To look into this, we'll be using this PhET simulation. And this time, we'll use this collision slab intro simulation. In this simulation, we have two objects, object 1 and object 2, which are lying along the same path horizontally. And upon playing the simulation, the two objects will basically collide. Hence the collision lab. Before we move on, please note how in this small data box below here, we have some useful information on both these objects' motion. From this, we can confirm how the momentum of these objects is simply the product of each object's mass and its velocity. At the top right corner of the page here, you have various options. You can click here to show these velocity arrows showing the object's velocities in these green arrows. Then click here to show the object's momentum in these blue arrows. Then the change in momentum, which appears after there's been a collision between these two objects, which would be the cause for a change in each object's momentum. Then you can click here to show the center of mass, here for the kinetic energy, then this values options, which pops up all this useful information in terms of the object's velocities and momentum at any point before or after their collisions. Then we can adjust the elasticity here, with inelasticity or 0% elastic being on the left and 100% elastic on the right here. Then we can click here to make your objects appear to have a constant size despite the actual mass stated here being different. Lastly, you can click on this momentum diagram button to show the momentum vector diagrams showing both objects' momentum and the total momentum. Then here we have our stopwatch and the playback, play, pause and forward buttons. Then these normal and slow buttons, which simply adds a slowed down version of the object's motion so we can see everything clearer. Once again, this is the collision lab simulation, and we'll be basically simulating various collisions between these two objects, object 1 and object 2. In this simulation, we have an isolated system where the resultant force and the total external force acting on these objects is 0. Remember, an isolated system excludes external forces like friction. In an isolated system such as this, the total linear momentum of these two objects will be conserved. This is stipulated by the law of conservation of linear momentum, which states that the total linear momentum in an isolated system is conserved or is constant or remains the same. This simply means that in an isolated system, the total linear momentum of the objects before the collision will be equal to their total linear momentum after the collision. Therefore, from this we get the formula: the sum of the object's momentum before the collision is equal to the sum of their total momentum after the collision, which gives us P1 plus P2 initially is equals to P1 plus P2 final, which therefore further gives us M1 V1 initially plus M2 V2 initially is equals to M1 V1 final plus M2 V2 final. This can be clearly illustrated in this collision lab simulation. We'll start with our object 1 having a mass of 1 kg and moving with a velocity of positive 1 meter per second. Remember, velocity is also a vector quantity and will thus have both magnitude and direction. We use the positive and negative signs to indicate the direction of our vector quantities, and this will be based on the direction we initially assume to be positive, which in this case will be this object 1's velocity, which is going to the right and will be going towards our positive direction. Hence, this object 2's velocity will be going to the left and will thus be negative. For our object 2, the mass is 2 kgs and it will be moving at -1 meter per second, which simply means it will be moving with a velocity of 1 meter per second towards the left. Please note how object 1's momentum before the collision is 1 kilogram meters per second. And for the object 2, its momentum is -2 kilograms meters per second. Remember how these are simply the product of each object's mass and velocity. Therefore, P1 plus P2 will be equals to 1 kilograms meters per second plus -2 kilograms meters per second, which will be equals to 1 minus 2 kilograms meters per second. And therefore, the total linear momentum before the collision will be equals to -1 kilogram meters per second. Now, after pressing play, we see that the objects once again collide. And we see that after the collision, as their velocities change, their momentum also changes. For object 1, its velocity is now minus 1.67 meters per second, minus because it is now traveling towards the left, and its momentum is now minus 1.67 kilograms meters per second. For object 2, on the other hand, its velocity is now positive 0.33 meters per second, since it is now traveling towards the right. And its momentum is now a positive 0.67 kilograms meters per second. However, when we consider the total linear momentum of both objects after the collision, we see that P1 plus P2 will be equal to minus 1.67 plus 0.67 kilograms meters per second, which gives us a total of -1 kilograms meters per second, and will therefore be equal to the total linear momentum of the objects before the collision. This law of conservation of linear momentum will also be true for inelastic collisions, as we'll see when we turn down our elasticity to 0%, which sets this to inelastic collisions. Let's reset. And once again, note how before the collision, object 1's mass is still 1 kg and its velocity is still 1 meter per second. Hence, its momentum is still 1 kilogram meters per second. And for object 2, it still has a mass of 2 kgs and its velocity is still -1 meter per second. Hence, its momentum before the collision is still -2 kilograms meters per second. Thus, the total momentum before the collision, P1 plus P2, is still equals to -1 kilogram meters per second. With our setting on inelastic, let's now press play. After this collision, we see that the objects now stick together and both move to the left with the same velocity of -0.33 meters per second. Object 1's momentum is now -0.33 kilograms meters per second, and object 2's momentum is now -0.67 kilograms meters per second. Once again, if we consider the sum of the object's total momentum after their collision, we get that P1 final plus P2 final will be equals to -0.33 kilograms meters per second plus -0.67 kilograms meters per second, which will then give us -0.33 minus 0.67 kilograms meters per second, which will also be equals to a total momentum of -1 kilogram meters per second for after the object's collision. So we see how even in an inelastic collision, the object's total linear momentum before and after the collision will be equal and the same.